Hey guys, so in this video we're going over our next project, which is currency correlation and minimum spanning trees. And so this project's a little bit more involved than the previous projects we've worked with, so I'm going to go stepwise, the first thing you need to do, then the next thing you need to do, so we can just break it down into these smaller steps in order to make the project a little bit easier. So the very first thing as a part of this project is we're going to be reading Dot Csv files. So what are CSV files? CSV files are just called comma-separated value files. So all they're good for is storing large volumes of data. So essentially we take a number, we separate it by a comma, and then we put another number. And we just keep doing that over and over and over, and we can have many rows of these comma-separated values. So it's just an easy format in order to store large volumes of data. And the types of CSV files we're going to be reading in this project is currency data files. So they're just going to have a lot of numbers that relate to how certain currencies changed over time. And it really turns out that we don't get too much insight as to how these currencies work within this project, so it doesn't really give any economical insight, but we're just using currencies because it gives us a large volume of numbers so we can better demonstrate what minimum spanning trees are. So yeah, if you guys are hoping that this project would give you a little bit more knowledge into econ, it's not really going to. It's just going to give us a lot of numbers to work with. And so yeah, we're going to be reading these CSV files so we can just get out a bunch of numbers. And I'm actually going to be providing you some code as part of this smaller subsection of the problem. It turns out within MATLAB it's really easy to grab all the numbers of a CSV file, but it's a little bit more tricky to grab the titles of each of the different parts of the CSV file. And so that's the code I'm going to be giving you. It's just going to give you an easy way in order to grab those titles. And so this code was actually given to me by my RLA when I took Chem 210, so I'm going to be continuing on the tradition by handing down this code to you guys. And so yeah, the first thing we're going to be doing is we're going to be reading off a CSV file so we can get this large volume of information. And we're going to take this large volume of information and we're going to be creating something called the correlation matrix. And this correlation matrix is going to tell us how the currencies are related to each other. And really what this boils down to is some basic statistics calculations. And so all those formulas for the statistics calculations are included within the PDF. So all you have to do is you have to encode those formulas and then repeat those formulas over and over and over again for all the currency data. And so this part's pretty simple. It's just going to be repeating something and then building this matrix. That's not a big deal. But from this correlation matrix, we're going to be creating something called an adjacency matrix. And what you end up doing is you're going to take 1 minus the correlation matrix. And what an adjacency matrix does is it tells us which nodes are connected to which nodes in a graph. And so, yeah, a little bit more on that later. So we've created our correlation matrix, and then we're going to be creating our adjacency matrix. So our adjacency matrix, as I said, is related to a graph. So that brings us on to our next part, minimum spanning trees. And well, in order to understand minimum spanning trees, we have to know what graphs are. And so let's go over what graphs are. So you guys are familiar with the type of graph that includes an x-axis, a y-axis, and like functions across it. But this is a different type of graph. This is a graph that includes nodes and edges. And so I've drawn a pictorial representation of a graph in order to better understand it. And I'm going to use the analogy of a city and roads in order to explain what graphs are to you guys. So as you can see here, we have 5 nodes within this graph. I've labeled them A, B, C, D, and E. And nodes are analogous to cities, right? We might have a bunch of different cities across the country. This could be Atlanta, this could be Denver. And that's all nodes are. They're like hubs of a graph. And then we connect nodes, or these hubs, by edges. And so these are edges. And so edges, I like to think of them as the roads that connect the cities together. So as you can see here, this edge connects Atlanta to Denver. And we can also add another qualifying factor to these edges, and those are called weights. And weights basically describe how large an edge is. And so again, using that analogy, this weight here for this edge between Atlanta and Denver might be how long that road is between Atlanta and Denver, or how long it takes to travel across that road to get from Atlanta to Denver. And so that's the basic nomenclature of graphs. We have nodes, which are like our cities. We have edges, which are like the roads that connect the cities, and then we have weights, which describe how long those roads are. And so from these graphs, we're going to be creating something called a minimum spanning tree. So what is a minimum spanning tree? Well, it's actually a subgraph. So we're going to be taking this graph and then we're going to be condensing it down into a smaller part of its whole. And what a minimum spanning tree does is it still includes every node of the original graph, but it only takes the edges which allow us from any one node to be able to traverse to any other node. So we're just trying to find the smallest number, or the smallest total weight of edges that allow us to, from one node, to still traverse to any other node within the graph. And so in order to find a minimum spanning tree, we're going to be using something called Prim's algorithm. And so I'm going to demonstrate on this graph qualitatively what Prim's algorithm does. And so the first step we do in Prim's algorithm is we choose us a random node. And so I'm going to choose A. And if you guys look in the PDF, when they explain this, they color the first node red. So I just put a little red X by it. And so the next thing we do after we choose a node and color it red is we look at all the edges that only have one red side. So as you can see here, this edge, and this edge only have one red side, right? Because they're only connected to one red node. And then out of those edges, we choose whichever edge has the smallest weight value. So I'm going to choose this one. And so then we also label this one red. And then once we choose that edge, we label the other side also red. So now we have an edge with two red sides. And then we repeat that basic process over again. We look at all the red nodes, and then we look at all the edges with only one red side. So what are those edges? This one only has one red side, this one only has one red side, this one, and this one. And then again, we choose out of that grouping of edges whichever one has the smallest weight value. So I'm going to say this one has the smallest weight value. So we choose that one. And then we label the other side red. All right, repeating the process again. Which sides only have one red side? Or which edges only have one red side? This one, this one, this one, and this one. So I'm going to choose, this is the smallest weight side. This one has the smallest weight. We label it off. And then we perform the algorithm one more time. All right, which are the only edges that only have one red side? Well, it looks like it's only these two now. And so then this one has the smallest weight. You finally choose that. So as you can see here, we've actually created the minimum spanning tree. We include all the nodes, and now we include the shortest total sum of edges that allow us from any node to traverse to any other node. So as you can see, if I start at node E, I can make my way up to any of the other nodes I want to. I can make it to A, I can make it to C, or I can make it to B. So from any node, I can get to any other node, and I only take the edges that sum to the smallest total amount. So that's all a minimum spanning tree is. And so what are we actually going to be calculating the minimum spanning tree on within this project? And well, that's the adjacency matrix. The adjacency matrix is going to give us information as to which nodes are connected and what are the weights of the nodes that actually are connected. And so all you're going to be doing is you're going to be performing Prim's algorithm on this adjacency matrix. And again, remember, this adjacency matrix happens to be 1 minus the correlation matrix. And so yeah, we've seen qualitatively how Prim's algorithm works. And it turns out this week it's going to be your job in order to translate this qualitative version into actual code. In the previous project, we've given you some amount of pseudocode in order to bootstrap you into actually programming those projects. This week, we're not doing that. We're leaving it more open-ended. We've given you a qualitative sense about how to do this, but now it's your job to actually translate this into MATLAB code and get Prim's algorithm to work. And so I wanted to give you a couple of tips in order to better accomplish doing this translation into actual MATLAB code. The first thing you definitely need to do is you need to keep track of the in and out nodes. And so what do we mean by in and out nodes? Well, in nodes basically correspond to which ones have red X's, right? Which ones have we looked at and we've decided to cross off? And then we also need to keep track of the out nodes. Which nodes have we not given a red X to? And so why is this important? Well, if we know the in and out nodes, we're able to figure out which edges only have one red side, right? And then from those edges, we can again determine the shortest edge to add in, and then which node to add into the in nodes and subtract from the out nodes. So this is very important because it gives us a systematic way of keeping track of which nodes we've already looked at, and then which edges only have that one red side. And then the second thing you guys should keep in mind is you need to create a blank matrix to update. So you're going to be doing Prim's algorithm, right? And you're slowly going to be adding nodes that are red X and then nodes that aren't red X, and you're going to be doing all these manipulations, right? Well, you want to make sure to not manipulate your original adjacency matrix. Anything that you want to add needs to be added to separate blank matrices. Because if you start manipulating your original adjacency matrix as you're performing Prim's algorithm on it, things are going to break, right? It's like working with something, and as you're working with it, you're changing it, right? That could lead to some disastrous consequences when you're writing your code. So just keep in mind, you never want to manipulate your adjacency matrix as you're performing Prim's algorithm, because that'll just lead to an incorrect solution. So that's about this week's project. I hope this video has helped. Do come to me in office hours. I'll see you guys in the RLA session, and I'll talk to you guys in the next one.